Uh, I think the links would be uploaded on this NPTEL website. Abhi. Um, I just need to check Gate NPTEL. Can you see my screen? I have started sharing the screen. See, you just need to Google Gate NPTEL and it will give you a website. I hope I am audible. So on this website you can see this live mentoring session and you can select this chemical engineering and here you will find the recording of those meetings, each of the meeting. That will take you to this YouTube where we have this recording of each of the lectures.
Or not?
In which we are, so these are the recordings of the sessions that we are conducting at this moment. So that are uploaded on YouTube and later on shared on this NPTEL website. We will start in couple of minutes. Let's say around 7:05. Harun, do you need the link for the recordings of the scheduled classes? You have written, can I get link for all the classes? Just let me check. Is the voice clear or is it noisy? Wait a minute. Just give me a minute. Am I clearly audible now? Or is there an improvement in the sound quality? Okay. So so on the NPTEL website, NPTEL Gate, you can just search in live mentoring session in chemical engineering. So right now I and Harishankar are only taking classes. So right now they are only twice a week. So on Monday Harishankar is taking the classes, and I think he's teaching this. He has started with mass transfer and he's right now teaching chemical reaction engineering, and that link you can join it by using this click button. And I am taking these classes on Tuesday 7 to 8, so that you can click from here. So these are the recording links of the previous classes. So right now only I and Harishankar are teaching, and we are not sure that next week there will be a class, but after that I think we need to reschedule all those meetings. So I think that will be informed. I hope that answers your questions. Okay, so let's start with today's lecture. So can you just write it in chat box? Have you studied the course Instrumentation and Process Control? So from today onwards we will be discussing the questions related to this instrumentation and process control. Okay, so I won't go into the details of each of this question, but I will just make you understand the basic concept that would be sufficient to solve the questions.
So that is how we will be going ahead in this instrumentation and process control. So just so from, as discussed, from today onwards we will be looking into this subject, instrumentation and process control. So by instrumentation, it is clear that we will be studying various instruments. So these are instruments are used for measurements. Measurements of various variables such as, let's say, pressure, velocity, temperature. So these are the physical quantities that can be measured using the instrumentation. So that we will be studying what all kind of instrumentation are there. So this isn't a much of what complexity. These are very simple instruments, and we just need to know their names and for what purposes are they used. And then the other part is process control. So that is the main part, and in most of the colleges this process control is being taught extensively, and this instrumentation part hardly takes 1 or 2 lectures. So this is the GATE syllabus that I have taken from the GATE website. So that includes measurements of process variables, sensors and transducers, P&ID equipment symbols. So this part you can call it in instrumentation. So the process variables in most of the cases can be pressure, velocity, temperature, volume, concentration. All of these are process variables that needs to be measured, and to measure these process variables we have these sensors and transducer that makes up to this instrumentations. So these are the parts of instruments. And then we have this P&ID equipment symbols, where P&ID means piping and instrumentation diagram. So let's say if I have a reactor and then there are these instruments to measure these physical quantities, so how should I denote them onto a flow sheet? So that is being studied by P&ID, piping and instrumentation equipment symbols. Then the main part starts from over here, that is process modeling and linearization. So, and then we have this transfer function and dynamic response of various systems with inverse response, process reaction curves, controller modes, control valves, transducer dynamics, analysis of closed loop systems including stability, frequency response, controller tuning, cascade and feed forward control. So in the initial few lectures we can start with this process modeling and linearization. In that I will show you what are transfer function, what are dynamic responses of various systems, then system with inverse response that we can do. So after we are done with this part, we will see how to control each of these processes by using these controller modes, control valves, analysis of closed loop system, stability, each of this part. So since you don't have in-depth knowledge of this subject, let me just start. So these are few of these courses that are available on NPTEL that you can take a look into to get the detailed knowledge. So the first one is Chemical Process Control by Professor Sujit Jogwal. He is from IIT Bombay. Then there is this Process Control and Instrumentation. So the first one is the video course. So we'll find these NPTEL videos on this subject. Then the second one is the Process Control and Instrumentation. This is a web course, so you can basically find the notes related to this subject. So if I just click on this link, here you will see notes related to each of this subject, each of this topic. So these aren't notes in depth, so this will just give you a brief overview for revising the subject. And then similarly there is this other course, Process Control and Instrumentation by Professor A.K. Jana from IIT Kharagpur. If you click on that link, here you will get the video lectures related to each of the topic. So just to give you a brief understanding, our subject name is instrumentation and process control. So in chemical engineering, you would have studied various kind of processes, let's say reaction, drying. You would have studied this under the name of unit operations: reaction, drying, simple mass transfer without a reaction. So let's consider a process. So I am having a CSTR over here, which has an agitator, and I am inputting my reactants over here, and then I have the product over here. So this entire thing I am calling it as process. So now I can model this equation using mass balance equations. Okay, so mass balance equations. Similarly, I am having energy balance equation. So all these equations related to this model are called as model equations, and they govern the dynamic of the system, that is how the system will proceed with time or any change in input. Okay, so in this case you can call this as input. Okay, let's say the flow of reactant as input, and the product, let's say the concentration of product as our output. So one of the main tasks of this subject related to this process control is to model this equation. So how can I model this entire process in which I am having input as, let's say, flow of the reactor and output as the concentration of reactor. So basically my output will be some function of input. Okay, so this is the model that we need to derive for this process. And ultimately, once I have this model, then let's say my main objective is to produce 100 kgs of product. Corresponding to that, how much my input should be, that I can find out using this model that I am having. So this part is known as modeling. Then there will be control of the process. Okay, so let's consider if I am having a jacket, cooling jacket in this, and the temperature of the reactant is T, and over here the temperature is Tj. Here the coolant is being fed coolant input, and similarly coolant output. Now see, with increase in temperature, the rate of reaction, the rate constant will increase, the rate of reaction will increase, and the amount of product formed will also increase. Now if I want to, let's say, control the formation of this product or the conversion of product, I can change the coolant, the cooling jacket temperature, via which the temperature of the reactor would be changed, and ultimately this product can be changed. So by changing this temperature of the jacket, I can control the concentration or the flow rate of the product, whatever desired quantity that I need to control. So this kind of loop is known as, we can call it as closed loop. And this entire phenomenon is known as process control. So first we model the process, and then whatever our objective is that we can achieve by changing the manipulated inputs, so via this process control. And see, now we are measuring the temperature of the reactor. Okay, so to measure the temperature of the reactor, we need some instruments. So there are this, let's say TT is known as temperature transmitter. There can be different type of temperature transmitters that measure the temperature of the process. So there can be this resistance temperature RTD kind of transmitter, which measures the resistance across the wire and then gives us the temperature. Then there can be pyrometer, which measures the radiation coming out of the surface, and based on their wavelength it will give us the temperature. So these are the instruments which are used to measure the process variables or the physical quantities. So that makes up our instrumentation part. I hope this much is clear. If you have any doubt, you can just write it in chat box. So this is just a basic idea of what the course covers. So one is this process modeling, so denoting any process via an equation. Then there is this process control, so what all parameters should I change by what values, that can be estimated by process control. And then there is this instrumentation part, so what all instruments can be used, so that will make up for this instrumentation part. So now let's take a look on this first question, and simultaneously I will teach you the concept behind that. Let me just check. Where can I find such web course for other subjects? So I think on NPTEL, if you just search these courses, you can get the web courses. Let me just show you. So from here on this NPTEL website, you can select chemical engineering. So right now we are studying process control. So you can just search for the course process control. Okay. So it will show you list of all these courses, all these courses. So the first one is process control and instrumentation. Then there is the other course, process control and instrumentation by IIT Guwahati. Then this is advanced process control, that won't be of use to you. Then this process control is mainly focused on design analysis and assessment, so this is also not useful. And this is the last course, process control chemical engineering. So you can click on each of this link. So from this you can see that these are the video courses. Similarly, if you click on this, then these are the web courses, so you can get the notes from over here. I hope that answers your question. So I don't think such web courses won't be available for most for all the subjects, but for process control it is available. And similarly, the last course, that is heat transfer, that we took, that was for that also this web course is available, so you can get notes from there. So now let's look at the first question. So the first question that we are discussing right now is from GATE 2012, question number 24, and the subject is this process. So this is related to process control, which we have started from today. The question is, a thermometer initially at 100 degrees Celsius is dipped at T equal to 0 into an oil bath maintained at 150 degrees Celsius. If the recorded temperature is 130 degrees Celsius after 1 minute, then the time constant of the thermometer in minute is dash. So in this given question, we have been given a thermometer which is at 100 degrees Celsius at time t equal to 0. Temperature is 100 degrees Celsius. And then we have this oil bath which is maintained at time equal to 0. Temperature of the oil bath is 150 degrees Celsius. Now after 1 minute, we have been given the recorded temperature is 130 degrees Celsius. So the thermometer will be recording the temperature, so that is the temperature of the thermometer becomes 130 degrees Celsius, and the temperature of the bath will remain same. Will remain same as 150 degrees Celsius. So consider this as a thermometer and we are immersing it into an oil bath. And oil bath is maintained at 150 degrees Celsius, and this temperature we are measuring from the thermometer. Okay. So if we had to plot this T, so here we have been given at a thermometer initially at 100 degrees Celsius is dipped at T equal to 0 into an oil bath. So let's say this is 100 degrees Celsius, and here consider T equal to 0. At this instant, the thermometer is dipped onto an oil bath, so initially the temperature of the thermometer was 100 degrees Celsius, but at this point suddenly there is an increase in the input. Okay, so this dashed line, this solid line is my input, so here it will become 150 degrees. So this is 150 degrees Celsius. But see, this temperature won't instantaneously measure this 150 degrees Celsius. So the temperature of the thermometer will take some time to reach 150 degrees Celsius, so it will follow such a kind of trajectory shown by this dashed line. Okay, so these are my measurements of the thermometer. Measurements of thermometer that we will denote it by Y. So these are the temperature measured by thermometer. And here in the question we have been given, it is recording a temperature of 130 degrees Celsius after 1 minute. Okay, and at t equal to 1 minute, let's say over here, we have been given the temperature is 130 degrees Celsius. And the question asks what is the time constant of the thermometer. So in process control we denote this time constant by tau, and that we have to find for this thermometer. So do you know what time constant is for this thermometer or in general? Okay, so I will show you what it. So we can just start with modeling this equation. Okay, we will modeling this thermometer. We will develop the process model for this thermometer, and then I will show you each of these features of this first order system. Okay, so let's just consider a mercury thermometer. And we are writing the process model. Okay, so let us consider this is our thermometer, and here we are having an oil bath, and this is the thermometer that has been filled with mercury, and then we will be having this wall of thermometer that is the glass wall. This is mercury denoted by Hg. Then we have the, let's say, any kind of fluid. So if I had to draw a cross section on this surface, I can see that this is our mercury, then there is this glass wall, and over here there is this fluid. And in this case, consider the heat transfer resistance of this glass wall to be negligible. So whatever the heat temperature of this fluid will be directly measured by the mercury. So in this process control subject, we usually denote the output. Okay, so output are the measurements. Output measurements by Y, and the input to the system as X. So in this case, we are measuring the temperature of any kind of system by using the thermometer. So that is my output. So the inert side, the temperature of the mercury, that is the temperature shown by the thermometer, we are denoting it by Y. So here the temperature within the thermometer is Y, and the outside, that is the fluid, will be my X. So X is my process variable or the input. So these are the temperature. So X is what you can call it as temperature of the fluid or system, and Y you can call it as temperature of thermometer or mercury. Okay, that is the temperature measured. And let's just consider for this for mercury we are having mass m and heat capacity Cp. Similarly, the heat transfer coefficient across this surface is H, and the cross section area or the heat the surface area for heat transfer, it will be area A. So if I had to write this enthalpy balance, okay, so let's just write the enthalpy balance. So enthalpy balance, you can write it as heat into the system minus heat out from the system. So basically whatever heat is being fed to the system minus heat out of the system will be equal to the heat accumulated. So this we are basically writing the energy balance equation or the enthalpy balance equation. So from heat transfer basic material balance, you can see that this will become HA, and the temperature difference across this system is X minus Y. So that you can write X minus Y, where X is the temperature of the surrounding and Y is the temperature of the fluid, as discussed earlier. So this is heat input minus heat output is equal to the heat accumulated will be responsible for the rise of the temperature within this, and we are doing the unsteady state balance. Okay, so this will be equal to m Cp, and the temperature of the thermometer will change with time, that is dT by dt, and in this case we are considering the temperature as Y. Okay, so let's just write it by Y. So I hope this much is clear. So this equation is known as the unsteady state and enthalpy balance. Okay, so what will happen, let's say initially if my thermometer is at 100 degrees Celsius and I suddenly keep it into an oil bath of 150 degrees Celsius. Okay, so the temperature measured by the thermometer initially it will be 100, and as soon as I put it into this oil bath of 150 degrees Celsius, the temperature of the thermometer will rise eventually, and ultimately it will reach a steady state value of 150 degrees Celsius. Okay, so these are the values measured by the thermometer. So let's say at T is equal to, let's say, infinity, the temperature of the thermometer will show as, temperature will become 150 degrees Celsius, that is. So this state we call it a steady state when there is no change in the output or the input. Okay, basically the process variables don't change with respect to time, that we call it as steady state, and that is achieved only after significant amount of time has passed. So for this case we write the unsteady state mass balance, we wrote the unsteady state mass balance as HA X minus Y is equal to m Cp so let's just write all these terms in capital. HA X minus Y is equal to m Cp dy upon dt. So these are the unsteady state mass balance, and if I have to write the steady state mass balance, so that we can write it as HA. So the steady state, after some point of time these values will become constant. X will become, let's say, will become constant at xs, and Y will become constant at ys. So this we can write it as m Cp dys by dt. But here we see that with respect to time, this temperature of the thermometer won't change after the steady state has been achieved. So after this it will just show me 150 degrees Celsius. So basically this dy by ds term will become 0. So that is, we can write it as 0. Okay, so from here we can see that this will also give us xs is equal to ys. That is, at steady state my output will be equal to the input variable, that is whatever the actual temperature of the system is, that will be shown by my thermometer. Okay, so let's just call it this as equation 1, this as equation 2. Now my main task of each of these process modeling equation is to find an equation of the form where I have this form: output is some function of input. Okay, so this is my main task, and in this case my output is y and the input is x. Okay, so now I need to find the relation between x and y I need to find a function that correlates the input x with the output y. So you can subtract both of this equation and it will give you HA x minus xs minus of y minus ys is equal to mCp d by dt y minus ys. So what this value show us is, let's say if I am having a value that is constant at xs and after some point of time I am changing the value till a new steady state is achieved, and this is x. So this deviation I am calling it as x minus xs. Okay, so this is what this parameter x minus xs signifies over here. So these are my perturbed variables. So how much change I am making from the steady state. Okay, so we can call, let's just replace it by x is equal to x minus xs and y is equal to y minus ys. So this perturbed variable I am just replacing by some simple value. So from over here I will be getting HA x minus y is equal to m Cp dy dy by dt. Okay. So what do we have over here? We have HA x minus y is equal to mCp dy by dt. So this entire thing is my process model. So this I can also write in terms of x minus y is equal to mCp upon HA dy by dt. Now this entire term mCp upon dt, if you find the dimensions of this term, it will be time inverse. So this we call it as time constant. Time constant or tau. So we can just replace this value by tau. So it will give us x minus y is equal to tau dy by dt. So this we can also write it as tau dy by dt plus y is equal to x. Okay, so this entire equation we call it as dynamic equation. And this system that we are discussing over here is called as first order system. So for any first order system, we will be having such we can model the process in such a form of equation, tau, where tau is the time constant, y are the output, and x is the input. Okay, now if I have to solve this equation, I can straight away integrate this, or else we can also use Laplace transform. So you would have studied this Laplace transform in your mathematics course, and in this process control we will be using Laplace transform in very extensively to solve each of these questions. So if I had to take the Laplace transformation of these equations, so that we can write Laplace transform of tau dy by dt plus y is equal to Laplace transform of x. So if we take if we take the Laplace transform of this equation, then we will be getting tau will be in bracket. So Laplace transform of any derivative is s ys minus y of 0 plus Laplace transform of this y will be y of s, and Laplace transform of x will be x of s. And this y of 0 will be 0, that is at time t equal to 0. We will be taking the output deviation, that is y of 0 we'll be considering it as 0. So that will give us tau s ys plus y of s is equal to x of s. So this I can also write it as just wait a minute. So this tau will be multiplied only on this first term. Let me just do it again. So we have this equation tau dy by dt plus y is equal to x. I am taking the Laplace transform of this entire term. So that will be Laplace transform of dy by dt plus Laplace transform of y plus Laplace transform of x, and this will give us tau s ys minus y of 0 plus Laplace transform of y will be y of s, Laplace transform of x will be x of s. So y of 0 we are considering it as 0, so it will become tau s ys plus ys is equal to xs. So you can take ys as common. Into tau s plus 1 is equal to x of s. So from here we can write this as x of s, y of s upon x of s is equal to 1 upon tau s plus 1. So here this y of s are my input, y of s is my output, okay. So this output upon x of s is my input. So we get this formula, that is 1 upon tau s plus 1, which is output upon input. So this entire ratio we call it as transfer function, or we denote it by g of s. So g of s is my transfer function. So this entire thing we need to remember. So for any first order system, so why do we call it first order system? So in this you can see that the power of s is 1. So that is s raised to 1. So that is why we are calling the system as first order system. So for any first order system, we can write the dynamic equation as tau dy by dt plus y is equal to x, and the transfer function we can write it as g of s is equal to kp upon tau s plus 1. So we are just replacing this 1 by kp. So where kp is the process gain, so that we are just replacing. So this is my general form of transfer function of the first order system, that is kp upon tau s plus 1. So ys upon xs. So let's say now I give an input to the system, okay. Now I am providing an input to the system xs. So we can use this equation to find the value of ys. So I have the process model of this equation. So this equation we will be using to solve our next question. So do you have any doubt in this derivation of this transfer function for this first order system? So here we looked into this derivation for this thermometer. So if you have any doubt, you can just write it in chat box or maybe unmute yourself. So kp is the process gain of the system, okay. So let me just show you. So see, in our case, I hope this slide, let's just call it as time, and x are my input. So initially I am having a thermometer that is kept at 100 degrees Celsius, okay. So this plot will show y and x simultaneously, and so this is my y, and the temperature of oil bath I am denoting it by x. So the temperature of oil bath is 150 degrees Celsius and the temperature of thermometer is 100 degrees Celsius. So let's denote by the temperature of thermometer by this x. So this is maintained at 100 degrees Celsius. Now as soon as I dip this thermometer into this oil bath, there will be an change in the surrounding, due to which this temperature is changing. So ideally the temperature should be this 150 degrees Celsius. Okay, but the thermometer will not simultaneously reach this temperature, it will take some time to reach this temperature to rise the level of mercury. So this is how it will proceed. Okay, so this X are the measurements or the Y, this process. So here you can see that we are changing the temperature by 50 degrees Celsius. Okay, so the gain that I am giving to the system is 50 degrees Celsius. So in this case, this 50 we are considering it as Kp. So this Kp, whatever the process gain or the change in the system that we are providing is the process gain or Kp. So in this case, it is 50. I hope that answers your question. Is that clear? Do you understand the value, the meaning of Kp? Kp is the process gain. So let's say if I'm increasing the temperature by 2 degrees Celsius and corresponding to that my output variable changes by 5. So then 5 by 2 will be my process gain. So corresponding to that parameter, the ratio will be Kp, process gain. So as discussed in the earlier slide, see the transfer function we derived it as Gs is equal to Kp upon tau s plus 1. Okay, and this is equal to y of s upon x of s. Now as mentioned in this case, we are introducing a step change in this in the input. Okay, so that is the value of xs will rise is changed suddenly. So if I had to find the Laplace of this function, okay, so this is my function, okay, f of t with respect to time, and this is my function, and if I had to find the Laplace transform of f of t, that is the step function, it will come around 1 upon s, where 1 is this magnitude. Okay, so if I have to now find the output, so that is I can write y of s is equal to x of s into Kp upon tau s plus 1. Okay, and x of s we can write it as 1 upon s, so this will give us Kp tau s plus 1 into 1 upon s. Okay, so this we are getting the output. So the output that we got from the earlier slide was y of s is equal to Kp upon tau s plus 1 into 1 upon s. Now this is in s domain. Okay, so this Laplace transform we find it in s domain. Now if I had to find the temperature with respect to time, that is output, how is the output changing with respect to time, so I need to take the inverse Laplace of this equation. So L inverse of this equation, and similarly L inverse of this equation. So if you take this Laplace inverse, so you need to change this into partial equation, and in mathematics you would have studied this, and if we take the Laplace inverse of this equation, then we will be getting y of t is equal to Kp 1 minus e raised to minus of t upon tau. Okay, so this is the output equation. If I am giving step input to my system. So okay, the input to the system was the step input, that is 1 upon s, and corresponding to that we will be getting some ys, and this ys in time domain is denoted by this equation, yt is equal to Kp into 1 minus t, tau. So for this thermometer, for any kind of thermometer, if I am having Kp process gain, let's just call it as 50, 1 minus and time constant, let's say if I am having it as 30 seconds, then I am having this function, that is y is a function of time. So with respect to time, how will the what temperatures will the thermometer record, that we will be getting from this equation. So this is the output equation, and few of the characteristics of this transfer function kp upon tau s plus 1. So if I plot the graph of this system, that is y versus t, then since this is a first order system, it will follow this kind of trajectory. Okay, so after some time this entire thing will become constant. Okay, so this will become a flat line, and this entire distance we call it as kp, and time constant we define it as time taken by the, let's say, this value, final value, as yf. Okay, so the time taken by the system to reach the 63.2% of this yf. Okay, so the time at which y is 0.632 of yf, so that will give me time constant. So let's say if my final temperature is 100 degrees Celsius, then over here it is 63.2, then time taken by the system to reach this 63.2 degrees Celsius, so this much amount of time we call it as time constant. So this is the physical significance of time constant, the time taken by the system to reach 63.2% of the final value. That is the physical significance of time constant, and kp, process gain, is the change in the input that we are providing. That is the process gain. If you have any doubt, you can write it in chat box, and then I think this much theory is sufficient, and we can move on to the question. So if you have any doubt, you can write it in chat box. I can explain it again. Just explain the graph once more. Okay. So I will just revise with all the equations. So what we are doing is we are deriving the transfer function of a first order system. Okay, so first order system, we looked for this thermometer case. Then similarly you can have this stirred tank heater. These are the examples of first order system. Okay, the stirred tank heater is, let's say, if I am having the water is going inside and exiting from over here, and I am having a heating jacket. So the input to the system, we can consider either the flow or the temperature, and the we can consider input as flow and the output as temperature. So this is also first order system. Similarly, if I am having a spring attached to a wall and then there is a block attached to this, then this also is known as this first order system. So these are this example of first order system, and in general we can write the dynamic model of the first order system as tau dy by dt plus y is equal to x, and for this transfer function is g of s is equal to y of x upon x of s is equal to kp upon tau s plus 1. Now I need to find how this transfer function behaves with respect to x. Okay, so I can give various inputs to this system. Okay, so the one input I can give is that I can constantly keep on increasing the input. Okay, so this is one kind of input. So this input is known as ramp input. The other input is I can just suddenly increase the value and again bring it back suddenly down. So this kind of response is known as impulse response. Then there is this other response in which I'm increasing it by step value and then keeping that as constant. So this is known as step value. So in this case we are finding the step response. So for the step response, xs is 1 upon s. Okay, so corresponding to that we can write y of s is equal to g of s into x of s, and taking the inverse Laplace of this equation, we can get this in terms of yt is equal to kp 1 minus e raised to minus t upon tau. Okay, now I need to I'm plotting this equation. Okay, so this equation I'm plotting onto the graph that I explained earlier. So this is time and this is my y. Okay, and the nature of this equation will be like this. After some value it will become constant. So let's say if t tends in this equation, if time tends to infinity, okay, so time tends to infinity, that is I will be putting infinity in this equation, so it will become e raised to minus of infinity. So that is 1 upon e raised to infinity, so that will become 0. So this entire term will become 0, that is yt will become kp. So that is this entire value at this point is kp. Okay, now I need to find the value of this tau. What is this time constant? So this time constant you can find it as this. So at some point, let's say 63.2% of this value, whatever the time taken by the system to reach the 63.2% of this value, that we call it as tau. So this time taken is time constant, and this process gain is, we are calling it as kp. So if you if you replace this yt as 0.632 and kp as 1, then you will be getting e raised to minus t upon tau, and if you solve this, then you will be getting time as tau. So that is how we obtain this time constant value. So this graph is known as first order response. Okay, so for first order system we can see that it will keep on increasing exponentially, and then it will become constant. So this is first order response. Okay, so now let's just quickly look onto this question. So in this question we are given a thermometer. So this is an oil bath and we have been given a thermometer. So thermometer, as we saw, is a first order system. Okay, so the transfer function is kp upon tau s plus 1 is equal to ys upon xs. And in this system, initially the temperature was 100 degrees Celsius, and at time t equal to 0, we are inserting the thermometer into this fluid bath of 150 degrees Celsius. That is, we are providing the step input to the system. Okay, so over here temperature is 150 degrees Celsius, and over here it is 100 degrees Celsius. So from this plot you can see that kp is 150 minus 100. Okay, so the process gain is 50 degrees Celsius, and the input that we are providing is the step input. So for step input, from the earlier slide we derived that yt is equal to kp 1 minus e raised to minus t upon tau. Okay, so this we derived from the from our derivation from over this equation, and over here we can just replace the value, that is 50 e raised to minus of t upon tau. So this equation we are having, that is y of t is equal to 50 1 minus e raised to minus t upon tau, and at now time t at time t equal to, let's say 1 minute. Okay, now at time t is equal to 1 minute, we have the recorded temperature as 130 degrees Celsius. Okay, so if we'll take a look onto this graph again, so this is how the temperature will proceed, and at here time t equal to 1 minute, we have been given the temperature as 130 degrees Celsius. Over here it was 100 degrees Celsius, and over here it is 150 degrees Celsius. This is at time t equal to 0. Okay, I hope this much explanation is clear to you. If you have any doubt, you can just write it in chat box. So from this equation we can see that what, from time t equal to 0 till time t equal to 1 minute, we can see that the rise in temperature is 130 degrees Celsius. That is delta YT we have been given as 130 degrees Celsius. So we can replace it, this YT is usually written as Y minus YS. So in this case, the steady state was 100 degrees Celsius for initial steady state, and at time t equal to T, the temperature is 130 degrees Celsius. So that is 130 minus 100 is equal to 30 degrees Celsius. So we will replace this YT over here. That is 30 is equal to 50 into 1 minus of e raised to minus 1. So we are putting this time t equal to 1 minute because at 1 minute the temperature is 130 degrees Celsius. So this you can now solve. That is 30 upon 50 is equal to 0.6 is equal to 1 minus e raised to minus of 1 upon tau. So this will become e raised to minus 1 upon tau is equal to 1 minus 0.6 will become 0.4. And then you can take log on both the side and it will give you ln of 0.4. So ln of 0.4 is minus of 0.9163, and you can inverse this and you will be getting tau as 1.09191 minutes. So this is the time constant that we get for this system. So in this question we have been asked what is the time constant. So the time constant for the thermometer is 1.091 minute. So let's revise. So we were given, we found out this equation YT is equal to Kp 1 minus e raised to minus t by minus t upon tau. And in this given question we were given that at time t equal to 0 the temperature was 100 degrees Celsius. At time t equal to 1 minute the temperature rose till 130 degrees Celsius, and the process gain from the graph was 50 degrees Celsius. So this YT we can write it as 30 degrees Celsius is equal to 50 from this plot 1 minus e raised to 1 upon tau. So we can solve this to find the time constant as 1.091 minutes. So this is how we derive the time constant for the thermometer. How do you recognize other? So okay, let's just again. So in this question, see, we have been given that from the plot you can see, if you draw the plot, that the temperature is see, initially the temperature was 100 degrees Celsius and then we are increasing it to 150 degrees Celsius, and the temperature of the surrounding won't change. So that is from the plot we can see that what the temperature is being maintained at 150 degrees Celsius. That is the step input. Now other kind of input can be ramp input. Okay, so let's just consider first the impulse input. So in impulse input, let's just consider if you have a oil bath of 150 degrees Celsius, and in the earlier case we are inserting the thermometer and keeping it there. So the temperature of that system will ultimately reach 150 degrees Celsius. But in impulse input, what we can do is we can quickly insert the temperature into this and again take it back out of this oil bath. So at that moment we can see that with respect to time, if initially the temperature was, let's maintain at 100 degrees Celsius, and at the instant where we dip the thermometer into this oil bath and again bring it outside the thermometer, we can see such a kind of peak. Okay, so this is the time duration within which we are keeping the thermometer in the oil bath. So this kind of plot is known as impulse input. Okay, and let's say if the area of the impulse is A and this width is B, then over here we will be having A upon B. So this kind of input we call this input impulse input of magnitude A. Similarly, then there is this ramp input. In ramp input, what we will do is we will keep on increasing the temperature constantly. Okay, so this is X and this is T. So if I had a heat source in this system, so in such a case the temperature of this fluid bath will keep on increasing. In such a case the temperature of thermometer will also keep on increasing, and that kind of input is known as ramp input. So by plotting this graph or just looking at the process or looking at the question, you can get an idea whether the given system is step input, impulse input or ramp input. But in most of the cases in this course, you will only come across this step input. So most of the numericals will be having this step input as the input function. So I don't think any of this numerical will have this impulse input or ramp input, but you can be asked the formula for this ramp input or impulse input. You can be asked to derive the formula for those kind of inputs, or else we will only considering step input in these courses. So in next lecture, so I guess this much is sufficient for today. In next lecture, we will be again looking into this thermometer example. So this is also related to this first order system of thermometer. And see, here you have been asked to find the impulse response of first order system. So right now we were giving the step input, and now in this case we are giving an impulse response. So we have been asked to derive the formula for that. For step input, we find out to be yt is equal to kp 1 minus of e raised to minus t upon tau, and for step input we have been asked what is corresponding function of this yt, that is this question asks. Then again in this question we have been asked to derive the transfer function for this unit step function. So for right now xs we considered as 1 upon s for this kind of plot, where here t was equal to 0. Now for this kind of plot, what is my input function, that we have been asked to find. So these are all the basic questions that you can expect. Okay, so if you have any doubt in any of these things discussed today, you can write it in chat box, or we can end today's call. So in the next class, we will be solving questions based on the theory that we discussed today. If you have any doubt, you can ask, or I guess this much is sufficient for today's class. Okay, so thank you for joining. We can end today's call. Okay, thank you.